Okay. Now, the next problem is this. There is a beam. Mesela bu problem daha iyi çünkü yönlerini falan çıkarabileceğiz burada momentin. Bir öncekinde ben rastgele koymuştum. Sadece bilgi olsun diye. Now look, there is a beam and loading shown. And in this problem, we are looking for the section NN. Okay, section NN. We are looking for the stresses at different points. Once at A, then at B, and then the largest shearing stress. The largest shearing stress. I want to say a few words about the largest location of the largest shearing stress later. Okay, now, obviously, in these problems, you have to start from statics. What is that? The shear force bending moment diagrams. Now, let's start with that. Okay, now, here is the beam, which you see. And let me draw this. Okay, hadi bir beam çizeyim. We have such a beam, right? And there is a external force of 180 newtons here. Okay, this one, it is given 180 kilonewtons. Then, very clearly, we have two reactions. One is this, and one is this. You don't need to calculate, they are very simple. 90 kilonewtons here, and 90 kilonewtons here, right? So it is given that this point is A, this point is B, and we are looking for the section NN. Now, if we extend this, let's draw the shear force bending moment diagram. Very simply, as you very well remember from the statics, the shear force diagram is this. So 90, 180, 90. Okay, a little bit in the middle portion like that. Right. 90 and 90 here because V is in kilonewtons plus. And then moment diagram. Okay, this is X, this is M. It is in kilonewtons per meter, say. So 0 here, maximum here, 0 here, positive. Okay, very simply, this is the shear force bending moment diagrams. Now, because of this, okay, this is the section that we are looking for. This is the section NN. At NN, we have a moment M, which we are ignoring its effect now, but there is a well-known shear force. What's the shear force at this cross section? It is 90 kilonewtons. Okay, it is 90 kilonewtons and positive. The shear diagram says that it is positive. Right. Now look, I am arkadaşlar biraz hızlı gitmek için şöyle yapacağım. Bir iki step atlayacağım. Now, we don't know the centroid of the cross section. Okay, so isterseniz yine de şunu bir çizeyim açıklayıcı olsun diye. Now, I am using such a coordinate system. I'm not going to write these details because we have just went through these calculations many times. I am using a coordinate system, this one, x prime, y prime. And using x prime, y prime, I am calculating y bar prime by using sigma yi ai over sigma ai. using three surfaces or three areas. Maybe this is the first one. This is the second one, and this is the third one, with their own centroids C1, C2, C3. Şu kadarını yazayım yeter. And at the end of this calculation, you can find that y bar prime is 65 millimeters. After determining this, okay, after determining this, I am just locating the centroid of the cross section somewhere here. Now this is the new C. And then I am attaching a new coordinate system that I'll be using in the calculations of the shear stress and moment, right? So this is my new coordinate system, and this one. These are Y and Z. Now I will continue with the blue coordinate system, but I know that this distance from here to here is 65 millimeters. Is this clear? Now, uzun uzun yazmayalım bunu artık biliyorsunuz. And then I can calculate I with respect to z-axis, which is the sum of iz1 plus iz2 plus iz3. So please calculate these by yourself. And moment of inertia of the entire cross section is 5,813,334. Now, for my shear stress equation, V Q over IT, I know I know centroid. Is this clear? Oldu mu arkadaşlar? Bunlar statik zaten şuraya kadar. Dolayısıyla burada zaman kaybetmek istemiyorum. Şimdi soruya gelelim. A. At the first part of the problem, I am looking for the stress at point A. Is this clear? Now, at A, I have the following cross section. I have this beam, the symmetric beam. Hep simetrik olacak zaten bizimkiler. Okay, like that. Burayı lütfen iyi takip edin. En kritik yeri burası zaten. Now, we know the centroid. Okay. So here is arbitrarily, that somewhere here we have the centroid. We have this distance Z. This axis Z and this axis Y. And now I am looking for the stress at point A here. Okay, this is point A. And I know that this is also the neutral axis. Arkadaşlar bakın. To find the stress at A, I am saying the same, I am repeating what I said for rectangle cross sections. Burayı iyi dinleyin lütfen. Teknik bir şey, yani çok teknik demeyeyim de pratik bir şey söyleyeceğim. Now, draw a line dividing this cross section into two, passing through A and parallel to neutral axis. This line. Is this clear? This line divides the cross section into two. Then I need Q. For Q, let me use this area. I am selecting this area for Q. Is this clear? Now I can use my equation. Why? Because I know that, şuraya yazayım, bakın, for this cross section, be careful, for this cross section, tau is equal to V Q over IT. This is our equation. What is tau? Now, here, arkadaşlar buraya bakın. Now, at this section, look at here. V is positive. If V is positive, tell me, is the shear force in the downwards direction or upwards direction at the cross section? Hangisi? Söyleyin lütfen.
Downward hocam.
Evet. Hatırlayın. Bizim shear force bending diagramda bunun sola doğru gittiğini varsayalım. Şöyle hatta aşağı doğru varsayacağız. Tamam. Moment pozitif. Onu da koyalım. Şekli tamamlamak için. Okey. Şimdi bakın deminki sorunuzun cevabı da geldi. Her neyse. Look. Therefore, tell me the subscripts. Tau is on a plane whose normal is in x direction, excuse me, direction is y, and since y is minus, there must be a minus in front of it. So I have Vy, Qz, Iz, and T. So for the stress, I need the following. First of all, I know Vy. It is given in the problem. Söyleyin, what is Vy? Shear force diagramına bakın.
90 kilonewton.
Yes, it is 90,000 newtons. Okay, what is T? Now, T is the distance of this red line, dividing the body into two. So what is T here? Yukarıdaki şekle bakarak söyleyin.
20 millimeters.
20 millimeters. T is the length of the line dividing the body into two, 20 millimeters. Okay, what is Q? Qz is the first moment of the area with respect to z-axis, that's yz. So it is area times y bar. What is the area? Area is this cross-hatch area. It is, look at here, it is, length is, yes, what is this length? 80 millimeters by 30 millimeters. I'm looking for this area, right? So area is 80 millimeters times 20 millimeters. What about y bar? Y bar is the distance of the centroid of this red area. Say it is somewhere here. I am just arbitrarily putting the centroid. This is the centroid of this area. And it is the distance between this centroid and z-axis. Okay. Remember, this length was 65 millimeters. This is 80 millimeters. So this distance here is 25 millimeters. Okay. So this is 25 millimeters and Q comes out as minus esasında şöyle yazacağım bir saniye. Şimdi arkadaşlar bakın şu şekle çıkalım. 25 nereden geliyor bir söyleyeyim tekrar size. Okay. This distance from here to here is 80. This z-axis is 65. Okay. Here is the centroid. So the remaining is 25. Clear. But when you look at here, bu sign şu açıdan hem önemli hem değil. Onu söyleyeceğim. Now, since centroid is below the y-axis, it is minus 25 millimeters. And Q comes out as minus 40,000 millimeter cube. Arkadaşlar beni iyi dinleyin lütfen. Do not use this minus sign in this equation. Just take its magnitude. Şuraya yazıyorum. Use magnitude. Why I am using this minus sign? Onu iyi dinleyin lütfen. If some of you, instead of using this red cross-hatch area, tries to calculate the remaining area, the Q of the remaining area, this Q would be first of all positive and equal to 4,000 millimeters, but be careful. While you are calculating Q, you will be composite approach. Probably you are going to use this first area and second area. If you don't use correct signs, because this Q1 is positive, but this area is negative. If you do not care about these signs, you end up with a minus wrong Q value. However, while using this Q at the end in the stress equation, do not use the sign, because that equation is not valid for that. Burası anlaşıldı mı? Umarım anlaşılmıştır. Şunları sileyim, kafanızı karıştırmasın. Oldu mu arkadaşlar? Bütün çekip karıştı galiba. Yani neyse. Bakın, bir daha tekrar ediyorum. İçinizde bazılarınız benim çizdiğim kırmızı alanı değil de geri kalanını kullanmak isteyebilir. Ve bu alanı da kompozit yaklaşımla kullanmak isteyebilir. Ve kompozit yaklaşımla kullanmak isterken küçük parçalara böleceksiniz. O küçük parçalarda Q'nun sign'ını dikkate almazsanız yanlış sonuç çıkar. Oldu mu arkadaşlar? O yüzden Q'nun sign önemlidir. Ama Q'nun sign'ını stres denklemine koyarken kullanmayın. So, if we are calculating Q by a composite approach, these signs are important to get the correct result. But at the end, whether it's plus or minus, use the correct magnitude in the above equation. Anyway, then, what is the stress? Stress is this. Tau xy, tau xy at A is equal to, the equation is above, V Q over IT. V is equal to 90,000 newtons. Look, I am using its magnitude. Q is 40,000 millimeter cube. I am using its magnitude. I is always positive, no problem with that. 5, 813, 334. T is always positive, okay. So 20 millimeters. I use everything positive, but then I have to determine the sign of the shear stress from the figure. It is a minus quantity because of our convention. As a result, it is equal to minus 30 megapascals. So now I found the stress. Use magnitude. Söyledim, bir daha yazmama gerek yok. Anlaşıldı mı?
Yani hocam composite approach kullanıyorken de Q'nun sign'ını dikkate almayacağız değil mi? Doğru anladım.
Alacaksınız.
Composite alacağız. Normalde mi almayacağız?
Denkleme koyarken almayacaksınız.
Tamam.
Kompozite kullanmazsanız onun için özellikle koyuyorum buraya. Kafanızı karıştırmak da istemiyorum ama şimdi şöyle söyleyeyim. Mesela böyle bir karışık şekil geldi ki önünüze. 2 tane Q'nuz var. Bu Q1 olsun. Bu da Q2 olsun. Tamam mı? Şurada ekseniniz olsun. Bu Q1, bu 2. Şimdi toplam Q, Q1 artı Q2 arkadaşlar. Bunları sign'larla toplayacaksınız. This is a positive quantity, this is a minus quantity. Actually, you are subtracting them, not adding them, okay? Because, say, this is C1, this is C2. So, this is, say, 100, I'm just writing, and minus 90. You calculate Q like that. Hadi bu da 190 olsun. What is the result? Minus 190. While putting the stress equation, do not use this sign. But while calculating Q from composite approach, you have to take these signs into account. Otherwise, the result will be wrong. That's what I'm saying. Okay.
Tamamdır. Teşekkürler.
Oldu mu arkadaşlar? Yani Q'ları kompozit yaklaşımda hesaplıyorsanız genelde bizim formüller o kadar komplike olmuyor ama ileriye dönük söylüyorum bunları. Tabii ki her bir parçanın sign'ına dikkat etmeniz lazım. Sonra biri 50, diğeri eksi 60 ise 50 ile 60 toplayamazsınız, çıkaracaksınız falan filan. Ama son bulduğunuz değeri oraya koyarken onu pozitif alın. Peki. Okay. Now, let's do one more step. Point B. Geldik buraya şimdi. Now, I am looking for the stress at point B, right? You see the point B there. So, okay, let's go quickly. For point B, I'm again drawing the figure. This is the beam, symmetric, okay, with respect to vertical axis. We generally use symmetric beams. And then the coordinates are as follows. Here is the coordinate axis that we have selected, which is centroidal, obviously. Don't forget. Okay. And this is the centroid. And in the problem, B is given somewhere here. Ben rastgele koyuyorum noktayı. Okay, here is B. Okay. This is B. Now look, the procedure is clear. I know that this is the neutral axis of the problem, right? Also. Then what I am doing is this. I am finding the distance. I am just drawing a line, dividing this body into 2 and passing from B, this red line. And now I have 2 areas. I can use 2 areas. Either this area, look, always use this area because it is simpler. Or the remaining. If you use remaining, You have to be careful about the sign of Q's because it's composite. But anyway, of course, this is simple. And here is the centroid of the area, somewhere here. Okay. And of course, I'm not going to go detail for the dimensions, but you can easily show that this distance, okay, şunu şöyle yazayım, bir sileyim. Bir dakika arkadaşlar. Sileyim, neyse. İki tane boyut yazacağım. Buraya da önce onları yazayım. Now, the centroid of this beam, this area, artık bunu siz kendiniz kontrol edin lütfen. Uzun uzun üzerine konuşmayalım. 50 millimeters from z-axis and the height of this area as given in the problem is 30 millimeters. 30 zaten problem vermiş yukarıya bakarsanız. Tamam. Centroid'de bulursunuz zaten kolay. Buradan sonrası önemli zaten. Okay, then look. In this portion, we have the same shear force. Because we are at the same cross section still. So Vy is equal to 90,000 newtons in the vertical direction. Tell me, what is thickness? Thickness is the line, the length of this red line. It is, again, 20 millimeters. What is Q? Q is the first moment of that cross-hatch area. A times Y bar. What is area? 30 millimeters you are seeing on the screen right now. It is width is 20, or thickness is 20 millimeters. This is the area. Now Y bar, as I've just shown on the figure, you can easily verify it. It's a geometric quantity. It's very simple for you. So it is 20 millimeters, right? Sorry, kaç yazdım? 50. Minus 50 millimeters. Look, I'm again using minus to prepare you for the composite areas. So Q is equal to minus 30,000 millimeter cubed. Then tau x y at b is simply. Peki bunun A'dan büyük mü olmasını beklersiniz, küçük mü önce? Onu söyleyin.
Smaller.
Küçük olmasını beklersiniz çünkü uca doğru sıfıra gidiyor değil mi? So look, magnitude, in fact it's a minus vector. Magnitude moment of inertia thickness d. Now I have taken everything positive. How can I determine the sign of the stress from our convention? The normal of the surface is positive. The direction of the stress is negative because Vy is negative. So it's a negative quantity. So it is minus 23.3 megapascals. Be careful about the sign. Soru yoksa son kısmına geçeceğim problemin. Peki.
Nereden belirlemiş sign'ı? Bir daha tekrar eder misiniz acaba?
Pardon, anlayamadım sorunu.
Sign'ı nereden belirlemiştik tam?
Arkadaşlar, sign'ı bildiğimiz kübik elemandan belirliyoruz. Yani bir kübik elemanımız varsa koordinat sistemi göre bizim shear stress burada aşağı doğru değil mi? Niye aşağı doğru? Çünkü kuvvet aşağı doğru şekilde bakın. Şuradaki kuvvet, bunu ben düzeltirken silmişim. Bir daha koyayım. Bakın. Demin arkadaşlarına sordum hatırlarsanız. Şimdi, pardon. Silinmiş bu. Şunu demin hatırlarsanız koymuştum. Bakın. Şu pozitif ne demek burada pozitif? Cross section'ın solunda bunun aşağı doğru olması demek. Bakın bunun vektörle bir alakası yok. Shear force diyagramda, bu arada pardon. Şu eksi olacak. Niye artı yazmışım? Her neyse. Burada enende şu pozitif bunun aşağı doğru olduğunu söylüyor. Biz bunu sol tarafsa kabul ediyoruz. Yani burada o detayda göstermedim ama tamam mı arkadaşlar? Bakın. İsterseniz şu cross section'dan önce şunu çizeyim. Now we have this beam. Which is going like that. Okay. Now, on this beam, from statics, you all know that her neyse. You all know that on the left we have this as positive, this Vy is positive, okay? And this moment is positive. Oldu mu arkadaşlar? Statikten biliyorsunuz bunu zaten. Hani size söylemiştim ya bir convention var diye statikte her ne kadar y ekseni pozitifse de tam tersini kullanıyor bu kitap diye. Kitaptakinin aynısını yazıyorum buraya zaten. Oldu mu? O halde bu pozitif bunu aşağı doğru gösteriyorsa buradan gelen stres de aşağı doğru olacak. Tau da aşağı aynı yönde olacak tau. Look, since this Vy from states in downwards direction, tau should be also in the downwards direction. Now, to write the subscript of x, I am referring to coordinate system. It is on the x plane whose normal is positive. Unutmayın şöyle bir koordinat sisteminiz var. Şimdi o soruyu soran arkadaş burayı takip et lütfen. Bakın şu x, şu y, şu z. Now x is positive, but y is, it is in a minus y direction, so it is sign is negative. Oldu mu? Cevap tamam mı?
Evet hocam, teşekkürler, sağ olun.
Yani statik, konvensiyon falan kullanıyoruz ama en sonunda koordinat sistemine dönüyoruz. O koordinat sisteminde bizim 1. chapter'ın sonunda kullandığımız konvensiyona göre sign'ı koyuyoruz. Tamam. Peki. Şimdi bakın mesela A noktasında bir kübik eleman çizseydik neyse onu sonra çizeyim. Şu soruyu bitirelim de. Gelelim C'ye. Vaktimiz kalsın. Now, part C is this. Look. The largest shearing stress. Şimdi arkadaşlar burada şöyle bir sorun var. If your cross section is symmetric and if almost uniform, let me say, generally the maximum shearing stress occurs on neutral axis. Just like, for example, in this rectangle which we discussed, it's very obvious that it is on the neutral axis. Very obvious. In this problem, again, due to symmetry and uniform cross-section, we expect it to be on the neutral axis. Is this clear? So now, for this part, if this is my beam, I expect the maximum shearing stress on the neutral axis. Burası anlaşıldı değil mi arkadaşlar? Bakın bu z, bu y. I expect it on the neutral axis. Tamam. However, buraya bir bakın sileceğim. If I had such a cross section, for example, you will see that maximum normal stress not occur on the neutral axis, but it occurs somewhere here. Is this clear? So it is dependent on the cross section. But if it is almost uniform like that, you can expect it on the neutral axis. Sadece aklınızda kalsın diye söylüyorum. Emin değilseniz check edeceksiniz arkadaşlar. Tamam mı? Ama rectangle'sa falan hiç tereddüt etmenize gerek yok. Anyway, now I said that it is on the neutral axis. There are two possibilities. One is using this area. Bakın, birincisi şu alanı kullanmak. Bu alanı kullanacaksam da şöyle parçalara bölüp kullanacağım. Tamam. Bu alanı özellikle kullanıyorum. Gereksiz olduğunu bile bile. And the other one is using this area. Oldu mu arkadaşlar? Bakın, aradaki fark şu. Now, I have to divide this into two by the red lines. Now, this is the red line that divides the body into two, if I am using this blue area. Şimdi arkadaşlar, if I am using this blue area, bana söyleyin lütfen Q'yu. What is Q? Q is equal to A times Y var. Oldu mu? What is the area? Kim söyleyecek alanı?
65 times 20.
Exactly. The area is, because we have already calculated the centroid, it is 8 times y bar. It is 65 millimeters times thickness, right? Okay. This is the area. What is y bar?
Eksi 37,5.
Onun yarısı değil mi? Minus 32.5 square millimeters. Oldu mu arkadaşlar? Yani şundan bahsediyorum. Şurasıyla bunun arası şu alan 32 millimeters. Okay, so Q is obtained from here. I'm just going to write the result as minus 42 times 250 squared millimeter cube. Could you tell me, if I am using this part, what is T? Yes?
20.
20 millimeters. Okay, look, this is the first solution, and you should do this, of course. But just to show you, I'm going to use the red line. Okay. Now, if I am using red line, I have 3 distinct areas. So, one area uzatacağım, yani sırf açıklamak için size. One area is this, C1. The other area is this, C2. And the other area is this, C3. Very obvious from the figure that this distance from here to here is 7.5 millimeters. And this distance from here to here, bunlar artık yani uzun durmuyorum size, rahatlıkla bunları bulursunuz. 25 millimeters, the centroid distances. I'm going to calculate Q from here. Okay. Gelin buraya. Now, Q. Sınıfta olduğu gibi bize soramıyorum ama yani birini söylesin lütfen bana Q'yu. Neydi Q? Şimdi ne oldu artık? Sigma AI YI. The first one, the first area. İlk rectangle kaç? 160 milimetre değil mi? Times 20 millimeters. The first area. What about Y bar? 25 millimeters. Oldu mu arkadaşlar? Then the second area. 20 millimeters times 15 millimeters. What about Y bar? Positive 7.5 millimeters. This is the area. Okay. But I have 2 of them. They are all the same. So if you calculate this, Q comes out as 84,500 square millimeter. Cube, sorry. Şimdi bakın. Bana şunu söyler misiniz? What is the relation? Şöyle bir daha yazayım. Okay. Q now here found as 84,500 millimeter cubed. Compare these two. Ne dersiniz söyleyin.
2 katı.
2 katı. Niye? Because if I use this, tell me what is T?
40 milimetre mi olacak?
Yes, look. In order to separate this red area from the remaining, I not only divide it from here, görüyorsunuz değil mi cursor'ı? Also from here. So now T is equal to 2 times 20 millimeters. So 40 millimeters. Therefore, Q over T is the same. Anlaşıldı mı arkadaşlar? Bir tanesi pozitif, bir tanesi negatif. Çünkü bir tane daha 42 var şurada. Toplarsanız 0 olmak zorunda Q'lar. Cross section'da. Şimdi gelelim soru çözüme. Hangisini isterseniz onu kullanın. Kırmızıları kullanalım. Okay. Now, tau x y max is equal to force. I am just using it as magnitude. Q, I am using 84,500. Okay. I, it is the same for the whole cross section. 5, 813, 334. Okay. And then T, 40 millimeters. If I had used the blue one, the first one. Now this is the second. If I had used the first one, Q would be 42,250, yes, half of it, but T would be 20, the result would not change. So the magnitude is 32.8 megapascals. Now let's check the sign. Normal is positive, direction is negative, so minus, minus. Okay. Any question? Şimdi buna çok benzer farklı bir şey yapacağız. Bu nötr eksene paralelse, if it's parallel to neutral axis, that's what we have done, and this shear stresses are very clear. I think Q is understood. BQ or IT is understood. Everything is clear. By the way, bir kübik eleman çizecektim size. Hangisini çizelim? Mesela B'dekini çizelim. Arkadaşlar bakın. Burası önemli. Esas gelmek istediğimiz nokta da bu yani sonuçta. If I draw a cubical element here. Bunu lütfen takip edin. Ben bunu size her zaman yani sınavlarda pek de yapamadık ama her neyse. Koordinat ekseni de şu. X, Y, Z. Bir tanesini çizelim, hepsi aynı. Şimdi at point B we have a shear stress tau xy. So you have to show this cubic shear stress on this face. Once you show this shear stress here, you all know that you have to show three more. Okay, one is this, the other one is this, and the other one is this. So this is tau xy, whose magnitude is 23.3 megapascals. Its direction is determined by the shear force acting here, Vy. Is this clear? Anything which is not clear? But we also know that there is a coupled moment with that. This moment creates normal stresses. So in addition to this tau xy, we also have a normal stress in x direction. So tell me, for B, is it tensile or compressive?
Tensile.
It is tensile. So I also have sigma x here and sigma x here. And this is mz. So this sigma x can be determined from mz y over iz. We know iz. You can determine y because you know B. And mz can be determined from our shear force diagram because here is the value of the mz. Okay. So you should know to show the stress state on such a cubical element always. Tamam. Herhangi bir soru yoksa şimdi daha önce biliyorsunuz nötr eksene paralel kesmiştik. Şimdi arbitreri kesip formülasyonu yeniden yazacağız. Var mı bir sorunuz? Peki. Okay. Then the next section is the following. This time yapabildiğimiz kadar yapalım. Longitudinal shear on a beam element of arbitrary shape. Arbitrary shape. By arbitrary shape, what we mean will be clear when you look at the figure. Okay. Now, Cengiz Han, bir sorun var mı? Cengiz Han Köse.
Yok hocam.
Thank you. Okay. Now, say that here is point P1, here is point P2. These are distributed loading, W. Always we are ignoring the points where these forces are acting. Okay. So we are just considering, bunu aynen yaptık esasında, bir kez daha yapıyorum. We are just considering an infinitesimal area from here. And then say that this distance is x away from here, and this distance is delta x. Now, the only difference from the previous case is that now on this element, now the figures are all the same with the previous one, so I don't want to draw them again and again. But look, now here, this is the slab that we are referring, right? Bir daha çizeyim, güzel olmadı. Şu kırmızıyı bir daha çiziyorum. Okay. This is the slab. And this is the side view. Okay. Now, by arbitrary shape, previously, we used a cross section or a section where the surface is parallel to XZ plane. Okay. Now we are just taking an arbitrary section. This is Y. So this is Z. Okay. And this is Y. Look, arbitrary section is this. I'm just taking such a section. Şöyle çizeyim. Daha önce hatırlarsanız Z'de paralel almıştık. Şimdi rastgele alıyoruz. Tamam. And then this section, say that, is defined by A. Şöyle bir A yazalım diye. Tamam. Gerisi aynı. Değişen bir şey yok. Again, we have distributed loading on it, like that, W. So let's extend this y-axis. And we have the shear force here, V, Y. We have this shear force here, Vy plus delta Vy as before. We have this moment Mz. We have this moment Mz plus delta Mz. Everything is the same. This time, the area is somewhere here. Pardon. Okay, here is the area, but we cannot see exactly because it's on the other side of the face. Okay, is this clear? Again, this is delta x. Yani çok detaylı çizmeyeyim arkadaşlar çünkü şekil aynen diğeri gibi. Delta x. And again, A, D, B, E, same with the other figures. So if you state, just look at that. Anyway, now here, further we know that this is the neutral axis and etc. Now here, if I take this area again, the important thing is the same. We have this slab, okay. İsterseniz biraz daha dar çizeyim, kafanızı karıştırmasın. Okay, şöyle yapalım. We have this slab here, right? And on it, we have distributed loading, like that, W. And here is the neutral axis. Yukarıda bir yerden kestik, tamam mı arkadaşlar? This is the neutral axis and also the other axis. So say that this distance is y sub 1. This distance is c. What do we have? Again, as before, this is b, this is a, this is d, this is g. Bakın, gene kestiğimiz yerleri mark ediyorum. Yukarıda görüyorsunuz zaten. Tekrar yazmaya gerek yok. This is F. Now, okay. We have the shear force VAF. We have the shear force DG. And because of the moments above, we have such a stress distribution here and another stress distribution here. We replace the moments with these. We replace the moments with the normal stresses created by the corresponding moments, right? Oldu mu arkadaşlar? Yukarıdaki momentleri bununla değiştirdik. Then, for force balance, what we need is a shear force here, which is delta Vx. Okay. So, since this moment is increasing or decreasing, whatever, we don't have force balance, and this force balance is satisfied this Vx. Okay. Now, şu denklemi de yazayım. Sigma x, daha önce yaptık aynısını, oraya bakın. AF in magnitude is equal to, bir saniye, is equal to mz, you know the equation, mz y over iz with a minus sign, but we are taking its magnitude. Sigma x on the other face, which is dg, in magnitude is equal to, again, minus this time mz plus delta m times y over iz. Okay. Anyway, the force balance should be satisfied. So sigma fx should be equal to 0. Then delta Vx, look at the above figure, minus sigma x AF, okay, times in magnitude dA, which is integrated over that inclined area. This should be plus, excuse me, minus sigma x dg, it is magnitude times dA should be equal to 0. Anyway, since the procedure is the same, since delta mz, as we discussed, is equal to dy times dx, what we obtain from here is that at the end, the same equation, delta Vx is equal to Vy times Qz over Iz times delta x. Look, the force equation is exactly the same, whether the area is arbitrary or parallel to the inertial axis. Okay. Peki şunu da yazayım durayım arkadaşlar. Buradan where, eğer vaktiniz var herhalde zannediyorum, I is the centroidal moment of inertia of the entire area. This is important. Inertia, not that particular area, but of the entire area. Of the entire area. Entire area is the entire area of the cross section. And Q, again, is the first moment of the shaded area. Shaded area in the above figure, you know the shaded area. Now, since this is the Vx, just a minute, kalemi alamadım. Okay. Then the shear flow is, shear flow aynısı zaten. Then the shear flow is, remember, shear flow is this force over the distance, and the shear flow equation is obtained as before, Q is equal to Vy Qz over İz. The same equation. Peki. Burada duralım. Bir dahaki ders devam ederiz. Aynı denklemden. Alanın eğri olması bir şey değiştirmiyor. Peki arkadaşlar. Bugün ne sağladık? Perşembe günü görüşmek üzere.